Hello and welcome to the Consilium Aquis Sulis Introduction to Control Center Automation, part of our series on train protection and automation. This course is intended for transportation engineers, operators, consultants, and managers, and consists of a single online video presentation which can be viewed at will. Please note that the course is for educational purposes only. Please consult the applicable standards for definitive information. There are no prerequisites to attending this course. The video will begin by explaining how route setting automates the task of moving points and commanding signal aspects, before describing how route setting can itself be automated. It will introduce train describers as an important feature of modern control systems and how they feed customer information systems. It will also explain how control centers can regulate the speed and platform dwell times of trains using automatic train operation. Finally, it will introduce rolling stock and train crew management systems. In early signaling systems, signalors physically moved individual points and signal aspects by human muscle power acting through levers, rods, and wires. The advent of electromechanical signaling enabled the task of moving individual points and changing signal aspects to be automated through manual route setting. In modern electromechanical and computer-based signaling systems, the signaler simply requests a route from one signal to another. Relay circuits or computers move points in the route via electric motors and illuminate signal lamps controlling entry into the route when safe. Route setting functionality enables routes to be set much more quickly, and thus enables signalers to control larger areas. This delivers benefits both in terms of improved capacity, as less time is lost in setting route, greater ability to make strategic regulation decisions with a larger area of control, and reduced staffing costs as fewer signalers are required. As with automation of driver tasks through automatic train operation, automation of signaler tasks through route setting places a higher level dependency on the signaling system. Interlockings, which were originally conceived as devices to prevent unsafe actions by the signaler, are now active agents in controlling points and signals. A fault in an interlocking now has the potential to lead directly to an unsafe state rather than simply fail to prevent one. And tragically, this has on occasion led to serious accidents, such as the 1988 Clapham Junction rail crash. The dependency becomes even greater in the case of automatic train operation, as the signaling system has direct control of the train. It is greater still in unattended operation, where there is no driver or train attendant to intervene if the signaling enters an unsafe state. On some lines, signalers do not even set routes for most train services. The routes are instead set automatically in accordance with a timetable or algorithms. One of the earliest technologies to do this was the program machine, introduced onto London Underground in the 1950s. Program machines were electromechanical devices that commanded interlockings to set routes over junctions in accordance with a timetable as trains approached. Towards the end of the 20th century, computer-based technologies for setting routes automatically began to be deployed on metros and main lines. Like program machines, these computer-based technologies can set routes in accordance with timetables. However, they can control much larger areas with more complex timetables than program machines. This enables them to be used on mainline railways as well as metro. They also support the addition and removal of services and can make basic regulation decisions when services are running late. Signalers can add services to an automated control system to cause it to set routes automatically for train movements outside the normal timetable. Timetabled services can be cancelled so that routes are not set for them automatically. Signalers can also disable automatic setting routes in specific areas in order to set routes manually for such trains. When two trains approach a junction over which their paths conflict, Regulation decisions can be made automatically in accordance with algorithms, for example on a first-come, first-served basis, or prioritized according to type of service, lateness of service, or to minimize overall lateness. Sometimes an algorithmically optimal decision at one junction can cause problems at others, and so be a poor decision in a broader context. For example, routing a freight train onto a line 10 minutes ahead of an express train may pose no immediate problem, but could cause unnecessary delay if the express train catches up with the freight train further down the line and cannot pass it. More sophisticated algorithms may therefore optimize across a larger area and even replan entire timetables in response to disruption. In order to route a train service correctly, whether manually or automatically, it is necessary to know what service it is. Originally, services were identified by means of specific configurations of lamps displayed on the front of locomotives and seen by signalers as those locomotives passed their signal boxes. Information about approaching trains was also communicated between adjacent signal boxes by bell codes. Trains are now identified by numeric or alphanumeric headcodes, which were originally displayed in large letters on the front of trains. In modern signaling systems, headcodes are presented directly to signalers on their control screen or panel by devices known as train describers. As a train moves through the schematic representation of the railway layout, so its headcode moves with it. At the start of each journey of a train service, its headcode is entered into the train describer for the section of track in which the train is stationed. When train detection indicates that a train has moved into an adjacent section of track, the train describer moves its headcode into that section. Train describers in different signaling control areas communicate with one another so that headcodes follow services seamlessly throughout their journeys. Train describers also share information with customer information systems, which use the information, along with pre-configured timetables, to indicate to customers which services are running to timetable, which have been cancelled, which are running late, and by how much. They also indicate which platforms services are expected to arrive on. Customer information systems can present their information visually on departure and arrivals boards, verbally through announcements and via web pages. Where automatic train operation or a connected driver advisory system is deployed, additional regulation controls are available. As well as determining which routes to set and when, control centers may also regulate train speed and station dwell times, and cause trains to skip or stop at specific stations. Regulating services in this manner offers a number of benefits, including reduced energy usage, wear and tear by discouraging drivers from driving faster than needed, better service regulation to even out gaps and slash or ensure adherence to timetable, as well as safety benefits from the reduction in speed and frequency with which drivers approach conflict points. As well as requiring routes to be set through railway layouts, train services require appropriate rolling stock to be available at the start of their journey, of which there are many different types, including locomotives, wagons, carriages, multiple units, rail cars, and engineering vehicles. Rolling stock periodically requires maintenance and cleaning, and if diesel-powered, refueling. Tracking rolling stock and providing the required vehicles at the required place and time for services is the job of rolling stock management systems. Most train services require staff to operate them, the exception being those with ATO at grade of automation level 4. Staff have different competencies, often connected to specific types of rolling stock and routes, and are rostered to work specific shifts, starting and ending in specific locations. Ensuring the suitably competent staff are available when and where required to operate services is the job of train crew management systems. Route setting automates the task of moving points and changing signal aspects in response to a request to set a route from one signal to another. This request may itself be automated in accordance with a pre-programmed, timetabled, and regulation algorithms. Train describers track train services throughout the journey, presenting their locally unique head codes to operators and customer information systems. In areas with automatic train operation or a connected driver advisory system, as well as setting routes, control centers may also regulate train speed and station dwell times and cause trains to skip or stop at specific stations.